So again, in talking about colligative properties, we looked at non-electrolytes in prior lectures. Now we're going to be looking at strong electrolytes. And the difference between strong electrolytes and non-electrolytes is that strong electrolytes, the number of particles is not necessarily equal to the number of, or the moles of particles don't necessarily equal the moles of the compound you have. So we have to include the number of particles that are formed when strong electrolytes dissociate in water. And the way we do that is by looking at something called the Van Hauf factor, which tells us the number of particles each compound, or the moles of particles each compound dissociates in. So it's like a multiplying factor that we use. So in all the colligative properties that we refer to for non-electrolytes, we're going to be adding this factor I to all the equations. And so again, I is determined by taking the ratio of the measured value over the expected value. And so this is how I appears in all the electrolyte, or the colligative property, or colligative properties equations. So you see, all we're doing is we're adding an I to each equation, which is the Van Hauf factor. Now for non-electrolytes, I equals 1. So that's why we did it included when we were looking at non-electrolytes in previous lectures. So everything else is the same, except now we have to incorporate the I when we're calculating the change in boiling point, or change in freezing point, or the change in vapor pressure, whatnot. Now there are two types of Van Hauf factors. There's the expected Van Hauf factor, which is based on complete dissociation of the compound, and that's in the light blue. So for example, when you dissociate iron 3 chloride, ideally you should get an I factor of 4. But as you'll notice when you do experiments, that you don't get the observed is not going to be the expected. It's always less than the expected. So not all of it would go completely to ions. So the expected is 4 for iron 3 chloride, but the observed is 3.4. So it doesn't get 100% dissociation. Now with magnesium sulfate, you see that the expected is 2, but the observed is 1.3. And what that tells us is, since magnesium sulfate only has 2 particles, magnesium ion and sulfate ion, that when it's 1.3, that tells us it's only about 30% dissociated. So 30% of it is ions, 70% of it is what you would call formula units. And so magnesium sulfate doesn't dissociate as readily as you would expect from ideal conditions. So ideally it would form an I of 2, but in experiment it only forms an I of 1.3. And since there's only 2 particles per formula unit, that tells us that only about 30% of magnesium sulfate dissociated. Now with magnesium chloride, it has 3 particles per 1 formula unit of magnesium chloride. And so we see that the observed is 2.7, the expected is 3. So again, the expected comes from breaking apart your compound into the different ions that make that compound. Sodium chloride again has 2 particles. It has a sodium ion and a chloride ion. So ideally, if it fully dissociated, we would have an I of 2. But in experiment, we noticed that it only has an I of 1.9. And again, since it's 2 ions make up sodium chloride, when we get a Van Hauf value of 1.9, that tells us 90% of sodium chloride dissociates, 10% did not. So it's still floating around as sodium chloride formula units. Now if we look at HCl, HCl is a strong acid that should fully disionize. And so HCl is made up of two components, H plus and Cl minus. And so ideally it should get an I of 2, but from experiment we observe an I of 1.9. So this tells us that HCl is 90% ionized. So 90% of it goes as ions, 10% remain as HCl molecules. And then glucose, which is a non-electrolyte, the expected and observed are the same. And so the way you would get the observed Van Hoff factor is you would make a solution of HCl. Say you make a 0.1 molal solution of HCl. You would then record the boiling point of that solution and then work backwards to calculate I. And that's what you do in the lab to determine the Van Hoff factor. You make a certain molal solution, you record its boiling point, and then you can calculate I from that and see whether the I is close to the expected or not. And again, the observed is always going to be less than the expected. Now we'll look at some problems. So here we want to know what's the freezing point of water when we have an 18.5% mass solution of lithium chloride. The Kf is 1.86 degrees Celsius per molal. And again, to determine the freezing point of water of this solution, the freezing point of solution equals the freezing point of solvent minus the delta Tf. And so we know the freezing point of solvent is 0 degrees Celsius. But we don't know delta Tf. That's our unknown. So in order to find the freezing point of solution, we need to find the freezing point, the change in the freezing point. And that brings us to this equation. Delta Tf equals Kf times molality times I. And so we know that Kf, it's 1.86. Molality, we don't know directly, so we'll put a question mark. Now I, since it doesn't mention that it's not an observed value of I, we can assume that lithium chloride fully dissociates. So if we write the dissociation of lithium chloride, we see that I is 2. So in order to find delta Tf, we need to find the molality, because it doesn't give us the molality. But what it does give us is the mass percent of solute, which equals 18.5. So now what we have to do is take the mass percent of solute and convert that to molality. So since we're given mass percent, we're going to assume 100 gram sample of solution. And then from that, we can get the mass of solute and the mass of solvent. So mass of solvent would just be 100 minus 18.5. That would be 81.5 grams. So that's 81.5 grams, and then we can convert this to kilograms. So now we have the mass of solvent. We need the moles of solute, and then we can calculate molality, because molality is moles of solute over kilograms of solvent. So moles of solute. We're going to need the molar mass of lithium chloride. and we get 42.4 grams per mole. So now we can find the moles of solute. And we get 0.439 moles of solute. So we have the moles of solute, we have the mass of solvent, we can calculate the molality. It's going to be 5.39. So now we have the molality, we can calculate delta TF. We get 20.0 or 20, yeah, 20 point. So now we have delta TF, we can calculate the freezing point of the solution. And so the freezing point of the solution is negative 20.1 degrees Celsius. So again, what we did is we determined that to find the freezing point of solution, we need to know the freezing point of pure solvent and delta TF. We didn't have delta TF, so we have to look at the freezing point depression equation, which is Kf times M times I. We had Kf, we could find I, but we didn't know molality, but we knew the mass percent. So the next step is to convert mass percent into molality. Once we found that, we could find delta TF, and once we found delta TF, we could find the freezing point of the solution. So here we know that the vapor pressure of water at 45 degrees Celsius is 71.93 millimeters of mercury. Calculate the vapor pressure of a solution that is 1.50 molal of potassium carbonate and the temperature at this temperature. And it says assume 100% dissociation. So again, Raoult's law. P of solution, or look at P of solvent equals the vapor pressure of pure solvent times, the mole fraction of solvent times I. No, that's not right. So first we have to calculate the change in pressure. So delta P equals the P of pure solvent times the mole fraction. No, hold on. So first we have to find the change in vapor pressure, which is equal to the mole fraction of solute times the vapor pressure of pure solvent times I. And again, here the P is the vapor pressure of pure solvent. There's a naught sign right here. So once we calculate delta P, then to find the vapor pressure of solvent, equals the difference between the vapor pressure of pure solvent minus delta P. So again, the naught sign means the vapor pressure of the pure solvent. So we need to find delta P. Well, we know the vapor pressure of pure solvents. (71.93 millimeters of mercury). Again, this is the pure solvent. P naught. We can determine I. So I equals the dissociation of potassium carbonate. And so we're going to get an I of 3, because when potassium carbonate dissociates, we get that. But we need to determine the mole fraction of solute. So this is where we're stuck, is how do we get the mole fraction of solute? Well, we have to use the molality and convert it to mole fraction of solute. So we need to convert molality to mole fraction. So if we're starting with 1.50 molal solution, we need to assume 1 kilogram of solvent. So if we assume 1 kilogram of solvent, we know the moles of solute. And we know the mass of solvent, 1,000 grams. Now for mole fraction of solute, this equals the moles of solute divided by the moles of solution. So remember, moles of solution is the moles of solute plus moles of solvent. Well, we already know the moles of solute. We know the mass of solvent, so we can determine the moles of solvent. Since this is in water, we know that the molar mass of water is 18, so we can determine the moles of solvent. We get 55.56. So now we know the moles of solvent, the moles of solute. We can find the moles of solution. And we get 57.06. So now we know the moles of solution. We can find the mole fraction of solute. .026.288. So now we have the mole fraction of solute. We can calculate the change in vapor pressure. And we get a change of 5.67. So now we need to subtract this from the vapor pressure of pure solvent. To get the vapor pressure of solvent in this solution. So the vapor pressure of water in this solution of a 1.5 molal solution of potassium carbonate is 66.26. So again, we needed to find the vapor pressure of a solution. We know that delta P equals X of solute times the vapor pressure of pure solvent times I. Once we find delta P, we can subtract it from the vapor pressure of pure solvent. So we found I by the dissociation of potassium carbonate. To find the mole fraction of solute, we had to convert molality into mole fraction. Once we found the mole fraction, we could find delta P, and then we could find the vapor pressure of solvent in this solution. Oops. And I forgot to start recording. So again, we have a 0.42 molal solution of nickel 2 chloride. It gives us the density, and it says it has a boiling point of 100.474. We want to find the osmotic pressure at 30 degrees Celsius. So again, in order to calculate osmotic pressure, we need the molality, the R, the T, and of course I. But here we won't use the idealized I value. We have to determine what the observed I value is. And so what we're going to do is we're going to use the information about the boiling point to determine what the observed I value is for nickel 2 chloride. And so we remember delta TB equals KB times molality times I. So we know KB we know the molality. We're looking for I, so we need to find delta TB. So delta TB is the difference between the boiling point of solution and the boiling point of pure solvent. So that would be 100.474, which is given to us minus 100. So now we have all the components to calculate the Van Hauf factor for this, the observed Van Hauf factor for this solution. So I equals and just by the way, your I should be greater than 1. And we get an I of 2.17. So again, this is the observed Van Hauf factor. And so it should always be less than the ideal Van Hauf factor, which would be 3. So now we have our I, 2.17. The last thing we need to solve for osmotic pressure is the molarity. So now we're going to take our molality and convert it into molarity. So we need to assume 1 kilogram of solvent. So if we assume 1 kilogram of solvent, we know the moles of solute. We don't know the mass of solute. We know the mass of solvent. We don't know and the mass of solution. We don't know. Because again, molarity is moles of solute divided by liters of solution. So in order to calculate molarity, we need to know the moles of solute, which we do know, and we need to know the volume of solution in liters, which we don't know. So again, what we're missing is the volume of solution. But in order to find the volume of solution, we need to know the mass of solution. So these are some question marks that we need to fill. So the mass of solute we can find because we know that we have the moles times mass, or excuse me, moles times molar mass gives us mass. We get 54.47 grams. So that's the mass of solute. The mass of solvent is actually 1,000 grams, not 100 grams. Let me erase that. Because it's 1 kilogram of solvent. So it's 1,000 grams. So the mass of solution is just the sum of the mass of solute and mass of solvent. So that's 1,054.47 grams. So now we have the mass of solution. We can find the volume of solution because volume equals mass divided by density. And the density was given to us in the problem. 1.25. So we get 843.6 milliliters. We convert this to liters. So now we know the liters of solution, we know the moles, we can calculate the molarity. We get 0.498 molar. So now we know the molarity, we know the R, we know the T, we know the I, we can calculate the osmotic pressure. We get 26.9, and this is in atmospheres. Let me double check. Yeah. So just to recap about what we did. So we needed to find the osmotic pressure, we need the molarity, the gas constant, temperature, and Van Hauf. Well, we had the gas constant, we had the temperature. It didn't give us the molarity or the Van Hauf, and it didn't tell us that it was an idealized solution or that it 100% dissociated. It gave us other information about the solution. It gave us the boiling point of the solution. So since it gave us the boiling point of the solution, we had to use that information to calculate the observed Van Hauf factor. So we found delta TB, we found KB, and it gave us the molality. So from that, we could determine the observed Van Hauf factor of 2.17. So now that we had the Van Hauf factor, next we needed to find the molarity. It gave us molality. We have to convert it to molarity. So since it's molality, we assume 1 kilogram of solvent. We could find the moles of solute. From that, we could also get the volume of solution. Once we knew the volume of solution and moles of solute, we found the molarity. Once we knew the molarity, then we could put all the pieces together and find the osmotic pressure. So in this example, we have a sample of mercury 1 chloride. It weighs 9.41 grams, dissolved in 32.75 grams of ethanol. It gives us the Kb. The boiling point elevation is 1.27. Is mercury 1 chloride a non-electrolyte? So mercury 1 chloride, if you didn't know, is made up of two ions. Excuse me, three ions actually, my bad. It's made up of mercury 1 cation, which is Hg2, 2 plus, and 2 chloride ions. So if it was a strong electrolyte, it would have an expected Van Hoff factor of 3. If it was if this compound was a strong electrolyte, it would have a Van Hoff factor close to 3. Now, if it was a non-electrolyte, the expected Van Hoff factor would be 1. So what we need to do is we need to determine what the Van Hoff factor is, and once we do that, we can determine if it behaves more like a non-electrolyte or more like a strong electrolyte. And so again, the Van Hoff factor close to 1, we would infer that it's a non-electrolyte. If a Van Hoff factor was, far away from 1, it doesn't have to be exactly 3, but like 2.5, 2.3, 1.9, that would indicate it's more like a strong electrolyte. So we're going to be using the delta TB equals Kb times molal times I. And we're solving for the observed Van Hoff factor. So we know delta TB, it was given to us 1.27 degrees Celsius. Kb was given to us, and we just need to know the molality so that we can find the Van Hoff factor. So the only thing that's missing here for us to find the Van Hoff factor is the molality. Molality equals moles of solute over kilograms solvent. So we know the kilograms of solvent because our solvent is ethanol. Let's go ahead and put it in kilograms. But we don't know the moles of solute. So we have to use the mass of solute divided by its molar mass to get the moles. So we know the moles of solute, we know the kilograms of solvent, we can find the molality. We get a molality of 0.609. Now that we have the molality, we can calculate the Van Hoff factor. So it's delta TB divided by Kb times molality. And we get a Van Hoff factor of 1.73. Let me double check. Yeah, or actually 1.74. So what this means is not a complete non-electrolyte. There are some moderately, or there are some of the compound does dissociate. But remember, the strong electrolyte, it'd be close to 3. Non-electrolyte, it would be somewhat near 1. You could, if we were just looking at a strong or non, I would go more towards non because halfway would be 2. So since this is less than 2, I would have to infer it's a non-electrolyte, or I would say since it's 0.74, maybe it's like a weak electrolyte because some ions do get formed. So here is H2G2Cl2 a non-electrolyte. I'd have to side on the area of caution and say no, because we have, it's not near 1, it's far away from 1, almost halfway between 1 and 3. So I would say maybe it's a weak electrolyte. If it was a non-electrolyte, it'd be very close to 1, like 1.1 or 1.05, something like that, where very little of it dissociates. But since it's 0.74, I'd be more inclined to say it was a weak electrolyte. Let me just show you one more example, and then we'll pause. So this example I wanted to show because it helps incorporate things we'll be learning later about acids. But we have a 1.35 molal solution, weak acid solution. It has a boiling point of 183. What is the percent ionization of the weak acid? And it gives us the Kb. So in order to determine the percent ionization, it's going to be linked to the Van Hoff factor. So in order to find the percent ionization, it's going to be linked to the Van Hoff factor. And a weak acid has 2 components. We'll use the general formula HA. So HA dissociates into H plus A minus, or ionizes, I should say, into H plus A minus. So if we were for a non-electrolyte, I would be 1. If it was a strong electrolyte, I would be 2. Now, based on the I value, the way we find percent ionization is if we take the I value the observed I value minus 1 times 100. So if I was 2, then you would have 100% ionization. If I was 1, then you would have a 0% ionization. But since it's a weak acid, it's going to fall somewhere between 1 and 2. So once we determine the Van Hoff factor, we subtract it from 1, multiplied by 100, we get the percent ionization, or how much of that weak acid ionized into ions. And so now we have to use the delta TB equation to solve for I. Now we know Kb, it's given to us. We know the molality, it's given to us. And delta TB we can find because it gives us the boiling point of the solution. and we know the boiling point of water. So now we can solve for I. And again, the reason we're solving for I is so that we can find out how much of this acid ionized. So we get I equals 0.83 divided by 0.53 times 1.35. And again, I should be greater than or equal to 1. It can't be less than 1. And so I get an I of 1.16. Let me double check. Yep. So now that we know our I, we can determine the percent ionization. And we get 16% ionized. So this is more like a weak acid. It's not fully dissociated like something like HCl, which is like 90% dissociated. It's like 16%. So you would say it's a weak acid, which is what it is. And so that's the percent ionization of this weak acid. So how much of the weak acid converted into ions. And so that concludes about strong electrolytes. Again, it's very similar to non-electrolytes, except you have to include the Van Hauf factor. And so that kind of concludes all about colligative properties. We refer to non-electrolytes and strong electrolytes. And so that kind of finishes up this chapter on colligative properties. So just one quick correction here. I wrote down the wrong KB. This should be 0.52. And so when it's 0.52, it's going to change it slightly. And we get 1.18. So this should be one. Let me just erase it. So start again. I used the wrong KB. So I equals delta TB times molality. I equals 1.18. And so percent ionization 1.18 minus 1 times 100 equals 18%. So it was only 18% ionized, which is a characteristic of weak acids. They don't fully ionize, or like strong acids, and they're not non-electrolytes. Very little of it ionizes. And this is how you can calculate how much it ionizes, by measuring its the boiling point of the solution. So that concludes, again, I just wanted to show this correction. That concludes this lecture over colligative properties. So on that note, Dr. Armand signing off. Until next time.